What up, what up? I'm the math teacher Goat, and today we are doing a full lesson on AP Precalculus 2.6 competing function model validation. Now, this sounds terrible, and it kind of is. It's just very weird. It's very strange. So, probably something you've maybe seen a little bit in Algebra 1, like you might recognize that maybe from Algebra 1. I don't know, it all depends. But a very weird, bizarre section. Make sure you go download the notes in the description, like and subscribe, all that good stuff. Let's get right into it. So lots of calculator stuff today. Okay, and we're starting right off the bat with just that. Use linear regression on a calculator to find an appropriate model for this data on the table. Then use that equation to find when x equals 12 and describe what that means in the context. So we've done this in my notes before where we do lin reg, we've done quad reg, cubic reg, exponential reg, and then we're going to store that equation in the TI-84 plus. So let's run over to our TI-84 plus, whatever that thing is called, and go do that now, see what it looks like. All right, so with all regression, we're going to hit stat first, we're going to hit edit, and all of our x values go in the left. So we had 4, 5, 7, so no real pattern here, just kind of numbers here and there. And then we get, let's make sure we don't screw this up, 130.79, 150.46, 189.80, 209.47, 248.81. Now what we're supposed to do is come up with that equation. Okay, so the equation is found by hitting stat again, going right to calc, and we're doing linear regression, so you can go down to 4 or just hit 4. Now before we even come up with the equation, we're going to use this equation later, so we're going to want to store it. So go to store reg eq, right, hit vars, go to yvars, hit 1 for function, 1 for y sub 1, and now it's going to be saved in here. Go down to calculate, hit enter, and you have yourself a not too bad looking linear function. And that linear function happens to be y equals, and are we using y? I'll have to double check. Yes, y and x. So y equals 19 points. All right. This happened in the last video. Okay, and it's going to happen again. I know what year it is. I know it's 2025, so I have to say it. Y equals 19.67. X plus 52.11. I'm not even trying to do that. Honestly, I'm not. I still don't understand the joke. Like Lamar Ball's height or something like that. What are we doing next? We need to find out what happens when x is 12. So there's two ways that we could do that. We could do that by hitting second graph by going to our table, scrolling all the way down to 12, and there we are. Now the other part, what do we get? 288.15? So the other way that we could do that, okay, the other way that we could do that is if we hit graph, we won't see it. Now, if we were to try to do this, second calc, because we've done this before, value, and type out 12, it's not going to work because our window isn't big enough. So if we adjust our window so that x goes out to 15, like that, now it'll work. We could do second value, okay, type out 12, and it'll be fine. Now, we don't have to do that. Since the number was friendly enough, we could just go to the table and hit down a bunch of times. But let's just say that the number was a decimal like 12.5 and the table couldn't work out. I just wanted to show you the other way to do it. But let's go back and write out our answers and explain what the one even means. All right, so the equation that we came up with was y equals 19. X plus 52.11. When we plugged in 12, we got 288.15. Now, what does that mean? That means $288.50 after 12 hours worked. Okay? All right. Okay. A pizza is removed from the oven and cools down for 5 minutes. During this time interval, the temperature is recorded once every 10 seconds. Somebody loves their pizza and their temperatures. The recorded temperature with respect to time can be modeled by linear, quadratic, or exponential for each of the three models. They appear to represent the data. Which of the following conclusions is best? Well, let's use common sense before we even draw it out. Okay. First off, once you take it out, it's at its hottest. Okay. Then 10 seconds later, still pretty hot. Still pretty hot. But what's going to happen is it's not going to go down linearly. It's going to start hitting an area called room temperature. And what it's going to do is as it gets closer to that, it starts to flatten out a little bit and will never cross that room temperature, what appears to be a horizontal asymptote. Now, this is not linear because it starts to slow down. This is not quadratic because it'll never go back up again. So this is going to be exponential because as it nears room temperature, the rate at which it nears room temperature starts to slow down and then will never officially hit room temperature. Or maybe it will hit room temperature, but it'll never go below that, and it takes its time getting there. So this is exponential because it kind of creates like a curve that flattens out like that over time. Okay? Okay. Use a scatter plot on the right to make a linear regression model for the line of best fit. Okay. Make a linear regression. Do I really need to? Maybe I don't need to. You know what? I think I'm going to have to. I don't know. I really don't want to. The numbers aren't that friendly. So I think what I'm just going to do with this one is I'm just going to draw a line of best fit. Because I don't think when I designed this problem, I don't think I designed it to be thrown into a calculator. We already did linreg. I don't need to do it again. This is me drawing a line of best fit. Okay? This is me drawing a line of best fit. Looking at this line of best fit, I am going to somewhat try to make an equation for it. So y equals, right? It looks like maybe my y-intercept is like 0.8-ish. So I'll go with that. And my slope appears to be kind of close to 1, but a little bit more shallow than 1. So, I don't know. There's really no points that I can use. There's no like corner points that I really can use. So, I don't know. If it goes... We'll say 0.8. We'll say 0.8 again. So, we'll say that the slope is 0.8, x plus 0.8. We'll go with that. Because it's a little more shallow than 1, okay, as you can kind of see. And there's my 0.8. Does the line of fit perfectly fit the data, but line of best fit perfectly fit the data? No, it never will if they're scattered all over the place. It's a scatter plot. So it's not like it's going to hit ... Does it fit it well enough where I can make accurate future predictions? Absolutely. Now that takes us to this next guy, okay, which is unique and is not seen a lot at all. Now, a residual is a measure of how much a regression curve vertically misses a data point. You take the actual measured data point and subtract the predicted value from the progression line. Okay, so here is residuals. Okay, these are all residuals. Here is a line. Now, a residual plot is a graph where the line of best fit is now the x-axis and plots are graphed according to its residual values. So if I'm given like an exponential regression, you can see how I have a dot above, below, a dot above, below, above, below, above. Where if I were to take this and try to straighten that out into a straight line, that's what it would look like. Now I can't really do it justice, so I'm going to quick put in a video of one of the shorts that I made. I'm going to quick have you watch that now and maybe it'll clear things up. A residual plot is a graphical tool used to assess the goodness of fit of a scatter plot or a regression model. It helps in identifying patterns in the residuals, which are the differences between the observed values and the values predicted by that line of best fit. The easiest way to understand what a residual plot is to take the scatter plot and rotate the line of best fit until it becomes horizontal. Now you have a residual plot. A common question that is asked is whether or not the residual plot represents an appropriate model. In other words, would the horizontal axis of the residual plot make a good line of best fit? Well, that's simple. If the dots on the residual plot show an obvious pattern, the answer is no, the model is no good. But if the dots represents no pattern at all and everything's scattered all over the place, then the residual plot does represent a good model for the data. And that's it. Don't forget to like and subscribe. So again, what we're doing is we're kind of taking this, pretending our hand is on one side here and the other hand's one side there, and we're bending it down so it becomes this straight line, right? And so the dots that are there are floating above and below where they normally are. So above, below, above, below, above, below, above, below. Okay, and you can kind of see the values up here now as you're moving along the x-axis. Okay, so here's my residual points. And here is my residual line. The difference between the predicted and actual values of these is the error in the model. Depending on the data and the context, it may be more appropriate to have an underestimate or an overestimate for any given interval. Okay, so you have your line, okay, and your line is your estimate versus the actual point. So the line is an underestimate of that. The line is an overestimate of that. The line is an underestimate. The line is an overestimate because it's above the point. The line is an underestimate because it's below the point, so on and so forth. So according to this, if I were to plug in 5, I should get, 0 according to this, which isn't true. But I actually get that point up there. So that's the underestimate, that's the error, stuff like that. The line of best fit will give another overestimate, will either give an overestimate or an underestimate. So we're going to run to our calculator again, and we're going to do a little bit of stuff right here. So remember, the error is the predicted minus the actual value. Okay, so why don't we come up with, let me see, how much am I going to need to do this in a calculator? Is the value predicted over? Okay. So I should be able to do A and B with the calculator and come back and then answer C based off of all that information. So a high school student is going to get ready for a basketball season by la. Each morning he records the number of practice shots he took and records how many he made. The table below represents the recording. So let's run to our graphing calculator and let's type in all of that information and see what we get. So once again, we have linear regression. So we're going to type in our x values into L1 after we hit stat and edit. So we took 100 shots that day. We took 75 shots that day. We took 120 shots. We took 200 shots. Lil John would love that. We took 50 shots and Lil John, that said 52, didn't it? Be careful. And then 300 shots. Lil John would really love that. Shots. It's a song. Look it up. Not a good one, though. My wife likes the song, though. Don't ask. 35, 22, 37, what else? 60, 20, 126. So we are going to make a linear regression model based off of this information. I don't remember if I need to save it, but I'll do it anyway just for funsies. Stats, calc, this is linreg, so that's going to be 4. Let's save it. So go to store regeq, vars, yvars, enter, and then we're just going to hit calculate. Okay, so the equation that we come up with is a messy one, but we round it to 3 decimal places. Y equals 0.4168, so 0.417. X minus 8.701. Okay, now B asks the question, what did it ask? Sorry, I'm scrolling through my notes here. Very unprofessional. Use the model from part A to find the error at t equals 50. All right, so the predicted value, okay, is what we get when we have 50. So if we were to go to my equation, okay, and let's do this. We saw this earlier today, and it's actually going to happen. I don't want to scroll all the way down, so I'm going to change my x max to 100. 110. I don't know why I did that. And what we're going to do is second calc value. And we're going to type in what happens at 50. So our predicted number for 50 is 12.139. So we'll do 12.14. Okay, 12.1. Actually, yeah, 140, because that's the way we're going to have to do it. 12.140. According to the chart that we have here, at 50, he actually did 20. So the error is going to be the predicted minus the actual. So error is predicted minus the actual. So let's go out of here and we'll do predicted, which was 12.140, so 14, minus the actual, which is 20. You hit enter, you get negative 0.786. Okay, so let's go back and do that and then answer part C. All right, so we ended up with y equals 0.417x minus 8.701. And at 50, we ended up with what we ended up with, which the error was negative 7.86. Now, the actual was 20. The predicted model gave us 12.140, which means the value predicted is a much underestimate of what we actually got because it's way below. Way below. Okay. All right, so not the best model ever, but you know what? Not everybody can be me. Oh, residual plots. They're gross. Again, you saw the video, and I think I described this just a little bit. When you're looking at a line of best fit in general, okay, and I'm just going to draw some general pictures, right? If I were to give you a bunch of dots that look like this, okay, a bunch of dots that look like that, all right, I could say, well, that looks pretty cubic to me, so let's draw a line of best fit that seems to cover it. And maybe not every single dot hits that line and it works out perfectly. But if I were to take this and try to bend it and stretch it out, I'm going to have dots like, you know, kind of above and below and stuff like that. So I know that my cubic was good, because if I were to bend this and stretch it out and keep the little dots hovering where it needs to be, there's really no pattern. It doesn't go like this. It doesn't go like this. Okay, it's just like the dots are kind of near it. So the shape of the residual plot, what does it tell us? Okay, how does the shape of a residual plot tell us if the regression curve is an appropriate model for the data set? Do the residuals exhibit a clear pattern? You look at this guy and the answer is no. There's no pattern, which means if this used to be a regular linear line, you're going to have dots that go like that, which means our line of best fit does a pretty decent job. So in a good residual plot, the residuals exhibit no clear pattern. No pattern is a good residual model. Looking at these pictures, though, a bad residual plot has an obvious pattern that doesn't seem to fit. It wouldn't make sense that if I were to say, here, look at these dots right here, draw a line of best fit and to have me go like that. That's what this guy is saying right here. That doesn't make any sense. Or over here, maybe you have dots that are going like that and someone said, draw a line of best fit and your line looked like that. That doesn't look right. See how it kind of goes up a little bit? So if it's giving you clear patterns, then it is not a good residual plot. If there's no pattern like what you saw up here, it is a good residual plot. So looking at this guy right here, and this is awful, a statistician recorded the pregnancy rate of 1,000 U.S. women aged 15 and 19. Holy cow, a bunch of pregnant teens. From that year to that year, a linear regression was used to develop a linear model for the pregnancy rate over time. The figure above shows a graph of residuals on the linear regression. Which of the following statements about the linear model is true? Okay, well, if I look at this, I see a clear pattern. Okay? It's a clear pattern. So if I'm looking at this, this is not a good residual model. It's not, because the numbers are clearly going up and down in a, well, I don't want to use the word that you're going to use, a sinusoidal way, but you don't know what that means is. Yeah, it is. So is the linear model appropriate? No. Is the linear model appropriate? No. The linear model is not appropriate because the residual plot demonstrates a clear pattern. I'm going to go with C on that one. Okay, it is like a very wavy looking pattern, and since it shows that pattern, this is not a good residual plot. We did a very bad job. Okay, so that's that one. And we're going to see more like it. A student creates a model for a data set. Which of the following could be an appropriate residual plot for their new linear regression? More than one answer may apply. You create a clear pattern, so you're no good. You create a pattern that goes down and to the right, so you're no good. You create a clear pattern that goes up and to the right, you're no good. You don't have a pattern at all. You're everywhere. You're fine by me. Why did I do that? That one's no good. No good at all. Whoops. All right. Quadratic regression curve. So quadrag. All right. One more time. Okay. So the altitude of the sun is simply a measurement of how high it appears above the horizon. In terms of an angular measurement, on Halloween, Mr. Bean. Oh, that guy. He's fun. He is fun. He does his best to measure the sun's altitude throughout the day. The measurement in hours since sunrise in the angle A is shown below. All right, find a quadratic regression curve round to 3 decimal places. So I'm going to have to run to my calculator for that one. I thought I was done. But once again, wrong. Use your model from part A to find out the error at t equals 10, and is the value an overestimate or an underestimate. So, calculator time. Let's go get it done. All right, we're doing quadrag, so stat edit. Let's put in our h values in the L1, so 0.5, enter, 3, enter, 7, enter, 10, enter, 11, enter. And then we have 6, enter, 32, enter, 41, 12, 0. Okay, so we're going to do quadrag and we're going to use it. So let's go to stat, calc, quadrag is 5. Let's go to store reg EQ, hit vars, yvars, enter, enter. Let's get our equation written down. There it is in all of its glory. We have y equals negative 1.458 x squared plus 16.164 x, and then minus 2.195. All right, so let's use that guy to find the error at 10. Now, a gentle reminder that the error is found by doing the predicted minus the actual. Okay, so predicted minus the actual, in this case, is going to be, what was the actual? Well, first off, we could write out the, well, let's go here and find the predicted. I care about what happens at 10. So if I go to my table, 10 ends up being what? 15.63. 13.63. So I'm going to go out of here and do my predicted, which is 13.63 minus my actual value, and my actual value at 10 was 12, and hit enter to get 1.63. Now, just like last time, this is asking if this is an overestimate or an underestimate. Well, if your predicted is higher than your actual, then the predicted is an overestimate. So let's go back, write all that down, and finish this guy up. All right, so we have h and a. So a is going to equal negative 1.458 h squared plus 16.164 h minus 20 or 2.195. That's my equation. When I did that, I ended up with 1.63. And since my predicted value was higher than my actual value, the predicted is an overestimate because it's positive. If the error was negative, it would be an underestimate. So is that it? Yeah, that's it. Residual models is kind of a bizarre topic. You get these pictures that you're bending them into straight lines and you're trying to be like, is it good enough or not good enough? And it's just like got a lot of regression stuff, which you would think we'd see more in Unit 1, but for whatever reason, AP people decided, nah, we'll put it here instead. So, very bizarre. Go to my YouTube and type out AP Precalculus 2.6 and watch some of my random videos to further your knowledge and give you more stuff, give you more ammo. Please like and subscribe. Thank you guys for watching. Have a wonderful, wonderful, wonderful day. I love you. Bye.